for this recording, after I have shown you in an earlier video to determine the Taylor polynomial T3 of x for the function f of x equal to x over 1 plus x and x equal to 1, now I'm going to show you how to estimate the errors when T3x approximates f of x on the interval from 1 to 1.5. And I'm going to show you that the error is less than 0.002. To do this, let's look at the PowerPoint slides. Okay, suppose the function f is a n plus 1 time differentiable on an open interval containing a point x. Then f of x is equal to f of a plus f prime of a x minus a, as usual, the Taylor polynomial plus the remainder term Rnx. How is Rnx here? Rnx is actually f differential f n plus 1 time at the point c over n plus 1 factorial times x minus a raised by n plus 1, where c is some point between a and x. And this remainder term, how big is this? It says that if the derivative n plus 1 derivative at the point c is less than or equal to m, it's bounded, then we know that the error term will be Rnx now, because fx will be Tnx plus Rnx, and the error Rnx absolute value will be less than m times x minus a n plus power n plus 1 over n plus 1 factorial. Okay, let's look at the solution of that problem. Okay, so to estimate the remainder after you obtain the T3x already, so T3x is equal to this term. So in order to get a remainder, so we know that f3 in many sense. Okay, so let me write here. We know that so f of x is equal to T3 of x plus R3 of x here. Alright, so in order to get R3 of x, you must get the fourth derivative. So we know that as we know that derivative of 3 times in the earlier calculation, the derivative of 3 times is 6 over in the earlier calculation f of 3 t time is 6 over x plus 1 power 4, which is 6 times x plus 1 power minus 4. So if you differentiate one more time, f of 4x will be equal to 6 times minus 4 is minus 24, x plus 1 raised to the power minus 5. And this is how we end up minus 24 over x plus 1, 5, power 5. Now, why is it useful here? Now, from here, we can estimate how is this m here. Can we estimate whether this is bounded? So, first of all, since our x is more than 1, since the reason x is more than 1 is for c is between 1 and x here. So, x is more than 1. So, why if we see x is more than 1 here? Let's look at the PowerPoint slide again, because we are going to estimate the point C. Alright, the point C in this case, C is a point between a and x where a is 1. So in this case, and why we say that x is more than 1, because our interval is from 1 to 1.5. Okay, so therefore x is more than 1 since x is between since x is between 1 and 1.5. So x is more than 1, then so x plus 1 or more than 32, so x plus 1 power 5 is more than 32, right? So 1 over x plus 1 power 5 will be less than 1 over 32. Okay, so the absolute value of f for x will be less than equal to 24 over 32 now, which is 3 quarter. Right, so that is how, and this is 24 over 32, right, 3 quarter. This is the m here. Now you can use a remainder estimate now. So we know that r 3x, magnitude of r 3x is less than or equal to m over 4 factorial x minus 1 raised to the power 4. So m is 3 quarter, so that is why we know m is 3 quarter, and this here, and 4 factorial is follow 4 factorial, right, follow here, and x minus 1 power 4. Now since x is between 1 and 1.5, 1 to 1.5, so x minus 1, notice that x between 1 and 1.5, so x between 1 and 1.5, so x minus 1 will be greater than 0, less than half, so x minus 1 power 4 will be less than 1 over 16. Now putting all this together, you'll find that the number is less than 1 over 152, so this is less than 1 over 500, and 1 over 500 is equal to 0.002. This shows you that the error is less than 0.002. Okay, so let's recap again. So all my working, after I continue T3x already, I find the fourth derivative, then estimate the fourth derivative, and find out that the m is equal to 3 quarter, right? This is the m is equal to 3 quarter here, and then from here I estimate using the estimation for the remainder, and you find that the error term is less than 0.002. This is the end of this recording.